So this is not actually what my topic is about government spying, but I will use toasters as an example because it's kind of a silly example to have a smart toaster. But you don't want your toaster broken into, you don't want your toaster spoofed, you don't want any of these things. And what I want to talk today about really comes down to this notion of identity. There's a lot of things with security. People talk about, well, we put TLS in, we do this, we do that. But if you don't have identity, there's no security at all. The communication, you're talking to someone, but you don't know who you're talking to. And what that comes down to, for example, the toaster talks to the cloud to upload the toast temperature or something. How does the cloud know that's the right toaster? How does the toaster know that it's talking to the right service in the cloud? TLDR, we need secrets on both sides. The toaster needs something the adversary doesn't have, and the cloud needs something the adversary doesn't have. And anyone who gets these secrets can pretend to be the party that had the secret. So to step back, how does the World Wide Web work? We go every day to https://www.google.com. What happens there? Well, they have a private key at Google. It's a secret, basically. Asymmetric cryptography allows them to say, I'm really google.com, and anyone who doesn't have that secret can't say that. So, interestingly enough, your browser doesn't know anything, and consequently, you don't really either. And it's actually a problem. This is why banking and this kind of thing is complicated, and you have so many passwords to remember. That's the thing that we've kind of come to, that you know that nobody else does, is passwords. It doesn't work very well. I mean, we have password stores, but that's a big problem, that people lose passwords. People use password 123. So to avoid having to log into your toaster in order to use it, the toaster is going to need its own secrets. How do you provision that? Does every toaster have a secret, or is there a toaster co secret that gets put into every toaster? And well, it's done both ways. There's a thing called a network secret that basically every toaster of a particular kind has this secret in it that identifies it as a toaster toaster. A lot of protocols actually do it just that way, and then they negotiate from that a specific secret for that device, so that you have this initial communication where they somehow decide, well, you're toaster number 37, and that gets associated with this secret. Thing is, if that network key gets out, if I can break into my toaster and steal that, then I can pretend to be any toaster, because all of the toasters have that same secret, and that's how they start out. So the real problem here that I want to focus on today, this is kind of introduction, is in order to do secure communication, we have to have secrets. And we have to store these in our devices. And there's a lot of ways. In IoT, there's a thing called PSK that's baked into a lot of protocols. There's a couple different ways of doing that. I was just reading about Google's IoT cloud, and with that there's a RSA private key that has to get put and provisioned into each device. Whether they're installed at provision time, later, if the key leaks, the device can be spoofed. And that's not just, if the key sits somewhere in, say, flash memory on a little MCU, and you have a buffer overflow in your network stack that you can then basically get access to arbitrary memory. These are kind of common exploits. Even if you can't run arbitrary code, maybe you can read memory and you can read the key out. And now you can pretend to be that toaster. The talk I gave earlier in the week about threat modeling, one of the big areas from that that is a pretty significant threat is the protection of these secrets. That there's a lot of ways to get them out of the device. And whether that's normal TLS, these low profile types of private shared keys, no matter what you do, there's a secret and you have to protect it. So I've come up with 4 solutions for this in our space. First caveat, I work for Linaro. These are going to be ARM specific. They're somewhat Zephyr specific, but not really. We are implementing on Zephyr, but these things work from on any kind of thing. And basically, I'm interested in your ideas other than don't bother, which is a frighteningly common solution to that. But if you've got brilliant ideas on other ways to do this, let me know. So, a little background. On the V8A, or V, it doesn't even just V8, the A processors, there's trust zone. And this is commonly used in these large processors. We have opt-T, which is a whole framework for doing all of this. And well, my talk was after, I didn't know it was going to be after yours, but this trust zone thing at the time is not really helpful with the M CPUs. But there is a trust zone for ARM v8M. Hopefully I got all of the spelling and capitalization right. Which this allows a trusted environment to separate secrets, but it's a new thing. You know, there's a lot of silicon out there that doesn't have this. In fact, nearly all silicon doesn't have this yet. Some other ideas. How does the Linux kernel handle this? We have user space, kernel space. Maybe we have some service in the kernel that can store the secrets, and then the user space processes can't get to that, or even just separate user space processes. One has the secret. The problem here is this kind of really wants an MMU. We do have something like this in Zephyr. It doesn't really like working with an MPU. It wants more RAM than these kind of targets have. But the real problem is this puts a lot of code on the wrong side of the barrier. If you're putting your secrets in kernel space, or even if they're in user space, you still have all of kernel space that you have to trust. And maybe your network stack has the buffer overflow in it, or I don't know why I like to keep blaming network stacks, but one of your protocol stacks, something like that. These exploits there can now still get to these secrets. You may be protected against the user's application getting to it, but there's still a lot of stuff. It really comes down to it doesn't satisfy the notion of least privilege, that you want as little of the code to have access to this as possible. So what else can we do? And again, I said that I come up with 4 solutions to this, not counting don't bother. So, real quick, these are the 4. The first one is throw all of the other hardware away and only use V8M. And I see the ARM people cheering for that. That's and honestly, yes, there's something practical to that. The second one is to improve the privilege separation. I'll get into what I mean by that. Another realistic one is to just use a separate CPU. And this is pretty common. These cores are really small. Put another one on there just to do your crypto and your secrets. And then we have this thing that made it into my title, this hypervisor-ish thing, which I'll get into in a minute. So, let's go over the first one. Use V8M. Sounds great. But we do have a lot of chips out there that have other things. And realistically, there's always going to be applications where this is a cost issue. We still have plenty of M0 cores out there. So this is a good solution when it's practical to use. As far as privilege separation, what we need to do to make that work is move more code to user space. And I'm talking about Zephyr here, where that sort of makes sense. This does get really complicated, though. There's still a lot of code in there that you have to trust. And this thing still wants RAM and something like an MMU to do its thing. The MPUs, I don't know if you're not familiar with this, the microcontrollers tend to have a thing called an MPU, where instead of mapping from pages to arbitrary pages with protection, you get some fixed number of regions that you can assign memory attributes to. And that can be as small as, I think, 7, something like that. So you kind of have to decide your memory. It doesn't work as well for arbitrary user processes, that kind of thing. As far as the separate CPU goes, that description is pretty simple. You put 2 CPUs in there, you then communicate between them and have that other CPU itself hold onto the secret. It's a great way to protect that, because no matter what you do on the main CPU, as long as your code is written correctly, you can't get to the secret. I think the real problem with this, the real danger is, it gets really tempting to just put more code over there. It's like, well, we got extra CPU performance there. Let's put our own network stack there. Not blaming that. I mean, it's a useful thing too, but now we also have code on that side of the barrier, and we are back to the same problem of how do we protect the secret on that processor from the rest of the code running on it. But this really can be a practical solution. You can stick a very small core there and just do your crypto with it, just do your secrets. And it works. So the last one, I didn't have a better name for this. Hypervisor-ish is kind of a weird word. But the basic idea here is to take what capabilities we have on a V7 processor and protect our secrets like we would, but only with what we have. So the way this works is Zephyr runs in user mode entirely. It doesn't have any privileges itself. And then it makes calls, traps, into this hypervisor for anything where it needs to do privileges. IRQs get complicated to handle. You kind of have to split them and handle a little bit of it in the secure side and then move it out. And the security, a big disadvantage of this, the security you get from this is only at a software level. This notion of security isn't happening on the bus or with the peripherals. So it's not the same level of security you're getting with TrustZone, but it's better than just it sitting in memory that you could read. There is a project, the Embed Microvisor, that kind of does this. It also does a whole lot more. It, for example, uses the MPU like a TLB to handle pages, and there's faults, and it swaps them around. But it's a good baseline to look at. So, I wanted to kind of end this with, what do I recommend? I'm supposed to go off and think about this stuff and then not leave everybody hanging, but recommend something. So, well, all of them. Basically, we need to support V8M where that makes sense. There's a lot of applications that's going to be the best way to do things. As far as kernel user space separation, larger systems where that makes sense, maybe it will. I honestly don't think that's as practical a solution as the others, but especially if, I don't know if somebody has, I only know of one Cortex-M target with an MMU in it, but if somebody makes some of those, that may be a practical solution there. I think it would be useful to define a dual CPU example with security. I mean, it's nice to say there's 2 CPUs, how do they communicate? What is the API like? I mean, in an ideal world, the APIs would be close enough to what's done on the V8M, the PSA, that, yeah, Jay?
No, just
sure.
at this point. Yeah.
Would like to do a dual CPU V7M example of TFM whereby the APIs are exactly the same. And,
Yeah.
I mean, we will be working on that at some point.
See, that's even easier. And then the other recommendation I would give is put some effort into prototyping this hypervisor and figure out, is it actually practical? What's the overhead of doing this? And an analysis from that, what do we gain from security and what don't we gain by doing it that way? And that's all I had to say. So, any questions?
Go back to your previous slide, if you don't mind. So that third bullet on there, does a TPM fall into that category?
Well, it depends. I mean, it can. The challenge with storing these kind of secrets is you have to have enough functionality to not... If you just store a secret on some other device and then your main API is to ask for it back, it's not really that useful to store the secret because the attacker can also just ask for it back or watch when it comes back. So you have to figure out what are the operations that need to be performed with that secret, whether it's key derivation of other keys, signing things, that kind of thing.
Revocation.
If you have these capabilities in the TPM, yes. If you have these capabilities in the TPM, then yeah, that would actually be a useful solution.
Secure elements would. Yeah, secure element.
I was going to say, I mean, that's the principle of a secure enclave and actually putting the secure side trusted firmware M code on the separate CPU. But as long as you've got the crypto services such that you can use the key in a way on that secure side to be able to do the operations that are needed so that it's never exposed to the non-secure side. And so, more than a TPM, a crypto island?
Yeah, and
A bit more ARM advertising, sorry.
there's trade-offs always. Security is often about trade-offs, and maybe the key doesn't come back, but a derived session key might come back, and an attacker gets access to just that session, not even the device, may be an acceptable risk in that kind of scenario. Other questions?
So, do you have some analysis on what people are doing on various systems? Because I think, it's okay, some ideas, but there must be some solutions out there which are using, well, not the top one, but out of the bottom three. Do you know if people are using something in production systems?
I'm not sure. That might actually be a better question for me to ask. If anybody has feedback, part of the problem with this space is there's an awful lot of solutions that are just there, and people don't talk about them.
So the third one, there's several. There's a number of ARM ecosystem partners that have dual core with a lot of the cryptography and all that built in, and they have special ways to isolate the processors. So those do exist. And have for about 3 or 4 years, maybe in some cases even a little bit longer.
My question is to try to understand the software.
Yeah, make sure we do talk into this, because when you go back and watch the YouTube videos, it's really frustrating to not.
So the question what I was asking is that obviously that hardware topology exists, but basically we need some idea on how people are structuring their software at the moment in order to be able to do an example which takes care of the problems that we see in the way these are.
Right, and that I don't really know much about. I mean, I think that's one of the reasons my suggestion was define an example of that, as you guys are talking about. That I think if there is an existing publicly available kind of way that that's handled, people are more likely to use that in a design, especially if there's a security analysis done on that too.
Okay, I think that's the TFM answer covered there. That there's definitely ideas about making sure something we attempt something D1V7 actually is in plans.
Yeah.
But there's no reason not to support containers, hypervisors, whatever else on the non-secure executing environment to add in an extra layer of isolation and separation there, if you want that for your system, if that makes sense for your application. So the kind of microvisor or hypervisor thing that you're talking about can coexist.
Right, and that's where this whole kind of funny, well, all four, that it starts to really depend on what your application is.
I'm going to piggyback on the same question. When you talk about the multi-vendor scenarios where you have different provisioning steps involved in the life cycle of the product, it gets a lot more complex.
Mm-hmm.
So probably it's a question to you and the rest of the audience, if anyone has very strong views on how it should be done, or anyone has some success stories to share.
Carefully.
Carefully, yes.
Yeah, I don't know if anyone has any comments on that. Kind of the focus that I work on is usually development boards, and I don't get a lot of visibility into how these things are manufactured. I mean, there's a lot of differences there. So, but it's important. So I don't know if anyone has any comments on that, or just throw that out there as something to think about. That provisioning does become pretty important because that's where your secrets come from. You know, if you look at, I've been spending a lot of time looking at protocols, and they define a lot of different ways of how you get the secrets onto the device. And there's a lot of stuff where there's a network secret there, and a not very secure network protocol that negotiates a device secret. And I think we need to do better than that. We need to come up with a way to manage having device secrets. So, anything else? Yeah. Where'd the mic go?
Have you checked the other situation when devices will not have any security inside of it, but the server will feed the security information during each session? So once the device connected to the network, it will pull the security information, so it will not belong to the specific device.
So let me try to see if I understand what the question is about there. As far as how does we have a secret. Are you saying how does the secret get protected when it goes out on the network? Or
No, I mean, like your toaster case, it doesn't have any secrets in the beginning.
Oh, okay. How
So
does the
once it's connected to the network, the like a server will provide the secret.
right? How do you do the initial provisioning? And yeah, I mean, it's a big problem. There's a lot of trade-offs there because the ideal world, you put the secret on there during manufacture, you keep a nice database of that, and the server knows about every toaster that exists. Practically in the world, there's a lot of devices that negotiate those secrets at the beginning, and if you watch that, you can often learn those secrets. And it's not as secure as it should be.
But it's always different for each session, so even if you will catch it up during the first session, it will be completely different for the second session. So it
Depends on the protocol. I mean, if you take, for example, LWM2M, it'll negotiate a secret, and then that's the device secret.
Yeah, the initial private key is static, and it's
Yeah.
only the session keys that are different. There are, if you don't do it at manufacture, which as you say is the right thing to do, there are companies that provide very secure key deployment systems. One example would be Trustonic. There are others
Yeah.
that have solved this problem in
I mean, you still
quite secure ways.
You do have some issues with some of these of there are attacks to basically trick the device into provisioning itself.
Manufacture's better.
Yeah.
Yeah.
I think that's the time we got. The thing was blinking at me, so. That's it. Thank you very much.